last year. I organized HydroML last year, and in my conversations with people, I started to understand more essentially of what other people were doing in terms of this large sample hydrology. And it became clear to me, at least the presentations that I followed, that there's definitely a shift from presentations focused on a little bit of theory with some data and then some results to presentations using all kind of fancy software and then showing results. So it was increasingly difficult for me to understand what is actually going on. And I thought, hey, that's not going in the right direction necessarily, what I think is a productive direction. Also, my opinion is that we cannot compete with AI companies. They can do things so much better, faster, they can scale, all that stuff. So then my wife reminded me at the end of the summer, said, Jasper, when we were at that conference, because my wife and daughter were with me, said, several times you told me that what is being presented, that you think you can do that much faster, because I forgot that idea. And so I was teaching last year. I'm on sabbatical now. So I was teaching in the fall, and then I walked out of my class somewhere at the end of November, and suddenly I got an idea. Oh, yeah, we can get the gradients, I think, analytically instead of using automatic differentiation. I think what we can do is we can essentially decompose that entire learning trajectory into different steps, and each step you can do analytically, and then you combine the steps, and then you're done. And by decomposing the problem in different subproblems, it gives a much deeper understanding of what's going on, and you can replace individual components much easier without having to rerun the entire automatic differentiation chain. So that is what this first paper is about. It's called Reclaiming First Principles, a differentiable framework for conceptual hydrologic models. Now, I must also tell you that I don't like the word differentiable, a differentiable model, because with some exceptions, all models are differentiable. So that word is almost meaningless, essentially. Again, there are exceptions, and the question is even whether a model needs to be differentiable to apply gradient descent methods. It needs to, I don't think it needs to be continuous differentiable, but that's more theoretical. But so the word, I don't know if I still like the word differentiable in this context, but because it's so popular, it's still here. And to be honest, when I wrote down this title, I didn't really think about it so much. But again, the word differentiable, I don't really know what it means that the model is differentiable. Okay, so the paper is about analytic gradients. So again, I had nice slides. I lost those, so I have to improvise a little bit. So what I'll do today, I'll go over the main theory, and then I'll show you a computer implementation in a software package where you can plug and play, you can download any data set you want, and I'll show you all the options it has. So, core idea and contribution. I learned that I have a tendency to write papers with a lot of theory, and reviewers may not necessarily like that. So I thought I need to be to the point. What's the core idea before people get lost? So we have a loss function. We have what's called a Jacobian matrix, and we have a gradient vector.
Jasper,
Yeah.
sorry, could you make the document wider
Oh
so
yeah, sure.
easier for people to read? Yeah, thank you.
That's a good. Thank you, Hoshin. The reason this screen is so much larger than my previous screen. Okay, so this is very easy to read. Great. I was worried about the scaling here. Okay, good. So it's curved as well, so I'm learning how to deal with that. Loss function, Jacobian matrix, and gradient vector. So this is a definition of a pointwise loss function. That's this one. Okay? So suppose we have a data set with n data points. And I use an index here. I run from 1 to n. So then this is my loss function at time t. Or I use time because we usually work with time series, but you can replace it with I. So you can also use spatial or is or x. You can use multiple variables, time and space, whatever. But the point being here is we have a total loss and we have a pointwise loss here, which is the summation, which gives us the total loss here. Now, this loss function you're all very familiar with. Common examples are the absolute error. Okay, so I use yt as the measured discharge at time t, and qt is the simulated discharge. So y is measured, q is simulated. So absolute error is you take the difference between the measured and the simulated discharge at time t and then the absolute value thereof. Other example is the squared error. You take the residual measured minus simulated, you square that, you multiply that with a half. You don't have to multiply with a half, but that's useful later if you compute confidence intervals and all that to keep the theory, but usually we only compute this part. Okay. Oh, here we go already. Oh, here. Where are we here? Almost. So that is standard stuff. Okay, here. Now, it's also good to keep in mind, and there is a mathematical word for this, but obviously you cannot write the Nash-Sutcliffe efficiency this way. And you cannot write the Kling-Gupta efficiency this way. Because if you compute those, you need to know what is the mean of the entire record. So you cannot do this pointwise. Okay, so that's good to keep in mind because that has consequences, for instance, calculating confidence intervals. Okay, there is an implicit assumption already in there in the Nash-Sutcliffe and the Kling-Gupta efficiency of what the residual properties are, essentially. Whereas here, you do it point by point, and then if you assume they're independent, you can still add that. Whereas with the NSE and the KG, that assumption is already baked in because you cannot write it as a pointwise loss, essentially. Now,
So, just a quick question, Jasper. It has to be pointwise in terms of the simulation and observation.
the function itself. Yeah, so I don't know if it needs to be pointwise in terms of.
Because optimizing mean squared error is the same as optimizing Nash-Sutcliffe, right?
Yes. Yes.
So Nash-Sutcliffe is pointwise in terms of the simulations, but maybe not of the observations, just because you need that mean, I guess.
I haven't thought that far, Joseph. Let me think about it. But you're absolutely right that if you do the NSC and the MSC, that's the same thing.
Hmm.
And so, yet you cannot write out the NSC as a pointwise function because it requires knowledge of the mean of the entire record. So it's something
Mean
to
of the
think.
observations only.
Yeah.
Hmm.
So it's interesting to actually think about that, what the implications are thereof. Like when I talk to Jonathan, for instance, he really doesn't like using a mean of the record because you usually may not have a record, or the mean may not be stationary, or but anyway, yeah, that's a good point. So if our loss function is differentiable, and most loss functions are, so if I look at this loss function or this loss function, you can differentiate these very easily. with respect to y, with respect to q. So I can take, if this is our y and this is our x, then you can compute dy dx. That's high school math. I'll show you that in a second. The same with this one, of course. So these type of functions are very easy to differentiate. NSE and KGE, same story. A little bit more work, but still straightforward. So if the loss function is differentiable, then what is called an M estimator is defined as the solution for which the total score. Oh, now we need to think. So in high school, we were taught that if you have a function, some function, and you want to find the minimum of that function or the maximum, that the way to find it is to find where the derivative of the function is 0. So same story here. If we want to know where this loss function finds its minimum, we're just supposed to find the point where its derivative is equal to 0. That's what you see here. So now we take the derivative at each point with respect to the entries that we're estimating, which the parameters, if you want to estimate other things, you can do it, but I use theta for the parameters that we're estimating. So you take the derivative of that pointwise loss with respect to the parameters. At each point, you compute that derivative, and then you take the summation thereof, of all those derivatives. Now, if we have, I use the symbol d for number of parameters. So if we have d parameters, then this is a vector that is d by 1. It's a vertical vector with d entries. Okay, so we call this the total score, where n is for the number of observations we have. Now, if you now go a little bit more to statistics, because that's where they look at convergence rates, consistency, and all that, then I think it's over here, yeah. Well, before I do that, let's first designate that if we look at an individual entry here, then that's called this one, g of yt. That's an individual entry. So it's the gradient here at a given time. I call that g of yt, where g stands for gradient. So this again is a vector, d by 1, and it has these entries. Okay? Now, total score is just the summation of the individual score. So if you have g of y1, g of yn, that's this equation essentially. If you sum them all up, then you get the total score. And so we want to know, going back to high school, where is that total score equal to 0 in each direction? And we have d directions, right? At that point, we find the minimum. Now, that so-called total score, those functions play a central role in generalized estimating equations. Okay, that's a whole field in statistics. And it says an estimating function, that's the total score, is unbiased if its expectation vanishes under the data generating process indexed by theta naught. Cool, what does that mean? Meaning that when you fit your model to data, that when you have n large enough, when you keep increasing your data set, that you converge to the data generating parameters. At that point, your score function attains a 0 value, meaning you find the minimum of your loss function there where the data generating parameters are. Now, this is always violated because the models that we use are too simple, meaning that the data generating parameters are outside our parameter space, okay? But I thought I'd make this connection because it's actually really important. It's not been explored, the connection I make next with M estimators, because I'll show you that next. Now, this is not new. And I dedicated this paper to Professor Solution, and in a slightly different context, and that's no surprise. They did this work 40 years ago. Hoshin was involved. So computation, the data, the computer power is very different, but essentially the same type of ideas they were working on, okay? Now, if we now look at our score function again, and we look here at the jth component. So this is parameter j. Remember, we have d parameters. Now we look at parameter j here. I call that entry gjn. So I'm just looking at one entry of this vector. Then that's equal to partial total loss, partial theta j. So how much does our total loss function change with the change in parameter j, sensitivity? Now you can write that out as a summation of a product. And you see here, partial loss at time t, partial qt, times partial qt, partial theta j. You see that the qt's drop out, and you have this left, and then a summation, and it gives you this. If you sum the LTs, you get your total loss. That's the first equation of the paper. And this holds for every individual parameter. So you can decompose your gradient into this product. Now, so let's look at this. This is partial LT, partial QT. Now, if you have this type of loss function, if I take the derivative of the loss at time t with respect to qt, that's fairly easy, right? Or I take the derivative of the loss at time t with respect to qt here. That's also fairly easy. That's a high school mathematics, right? So that's very easy to do, meaning that this part is purely analytical. As soon as you know your simulated time series, you can compute this component. Now that leaves us with this component. What is partial qt? So what is the change in the discharge with the change in parameter j? So how much does the discharge change when I change parameter j? And you always need to think about this as local in the parameter space. These are nonlinear models. If they were linear, would not be a partial. This just would be constant over the whole parameter space. Wouldn't depend on the parameter values. But it's all local, right? Based on the current parameter values, if I change theta j a little bit, how much does then the discharge change? Now, that is much harder to obtain, but this component we can get analytically. Now, you can write this also in this form, but now we're talking about the total score. I'm sorry for the dog. He's downstairs. My daughter badly wanted a dog, and yeah, and now we are spending most of the time with it. But turns out to be normal in this neighborhood or so, and we talk to other parents. Total score is the derivative with respect to of the total loss with respect to theta. Now, so you can write the same equation in this form, okay? But now we're talking about this is now becoming, now we need to think. Here it's a scalar. This is a scalar. This is a scalar. And then you do the summation. In this case, we're now doing the whole vector at once, right? This is a scalar. Now we do the whole vector at once. So now we need to think that this becomes a vector probably, transpose. And this thing, I need to think about, this is still a scalar times a vector. Now this part here is the row number t of what we call a Jacobian matrix. So now we're going to replace this thing here with this symbol. And what is that Jacobian matrix? Here is your Jacobian. The Jacobian with respect to the discharge, simulated. It's not the Jacobian of the measured discharge, even though the two are directly related. But it's the Jacobian of the simulated discharge. I use Q for simulated. Is the derivative with respect to theta of your simulated discharge time series. And these are the individual entries. So this is a vector transpose. So we get this first row. And then this is a vector transpose. We get the last row. So what is that? The first entry of your Jacobian is how much does the first simulated discharge change when I change the first parameter? Then the last entry, so this is the first parameter, second parameter, last parameter. And this, for the first parameter, first discharge, last discharge, all with respect to theta 1. So they're different columns, okay? Now, this formulation with the summation is not particularly ideal, but you can use rules of matrix algebra and you can just write it this way, meaning that the gradient total score or the gradient with for given parameter values is equal to the Jacobian with respect to simulated discharge transpose times this vector, which is this thing here. And let's look at whether the dimensions make sense. The Jacobian is an n by d matrix. If I transpose that, I get d by n. If I multiply d by n by an n by 1, I get an n by 1 vector. Sorry, d by 1. So d times n by 1 is a d by 1 vector, and that's this one. D entries. This one. That's what comes out. Okay, so now we have written the gradient as a product of a Jacobian transpose and a vector, loss sensitivity vector. Now, let's look at this loss sensitivity vector. This one. Now, I already showed that if you use a squared residuals type of loss function, that if you take the derivative of your total loss or your point loss at t with respect to simulated discharge at time t, that's an easy math. That's simply minus your residual. So this thing you can put in here for your entire residual time series. So again, you have parameter values, you put them in your model, you create a simulation, simulated discharge, and then you compute your residual, and that's this one, for a squared residual loss function. Now we only need this one. This is the key. How do we get that Jacobian? Now we can do that numerically, right? But we don't want to do that because then each time you need to do additional model simulations. You perturb the first parameter, the second parameter, the third parameter. You see how much the discharge changes, and that's how you compute that Jacobian column-wise. But that's all additional model runs. Takes time. So is there a way to get this analytically? Yes, there is. Now, why do we want to do this? Once we have our gradient, we can do gradient descent, right? So if we can get our gradient easy, that means we don't have to do SCE. And there's nothing wrong with SCE. It's a very good algorithm, certainly for hydrological models. But if we have the gradient and we could get that really cheaply, then you can use the gradient descent method, where you just start at some parameter values, you compute the loss, you compute your gradient, and then the next one, the next one, the next one. So that's how you update, where this is the learning rate, and you can make that iteration dependent. So that's why we want the gradient. We can train really quickly. Now, if you look at the literature in mathematics, they actually solve this problem, okay? If you write your model as an ODE system, then you can get your Jacobian for free. So let's look at that. So if this is our hydrological model, this is a vector valued model. F, you see here, and that's why I like notation so much, because everything is in the notation. It's all in there. If you see the details, it's all in it. F here is upright, lowercase, meaning this is a vector valued function. It doesn't return a scalar, it returns a vector. X is a vector. X is the vector of state variables. This is time. So how much do the state variables change as function of time? Is this vector valued function with input the states, the parameter values, and the current time. And of course, you have precipitation, you have all these other variables that I ignore here, but you get the point. So x is a vertical vector. So when I talk about a vector x or a vector theta, they're all vertical vectors, okay? And it has m entries. And now there's a key, one step we need to make before we can get the Jacobian, and that is that here a step. So let me pull up something else here. Most hydrologists, they write here. So here is an ODE form of a simple model. In this case, it's a HIMOD of Doug Boyle and Ho Shin. It was in Doug Boyle's PhD thesis about 25 years ago. P is precipitation. EA is actual evaporation, actual evaporation. Unsaturated zone, fast reservoir, fast reservoir, fast reservoir, slow reservoir. Now, what's now the point? The point is, to make all this work, you need to add discharge as a state variable. Now, how do you do that? For those working with ODE systems, you may have come across this problem that if you want to use built-in ODE solvers, that they don't work for hydrological models, because ODE solvers only give X, the state. They don't give Q. They only solve for the state. They solve for all the fluxes, but whatever fluxes it solves for is internal in the ODE solver. And we want to get Q out. We want to get the discharge out, right? The sum of QS and QF, that's the discharge. So once you struggle with that, you're not going to modify really deep down in the ODE solvers that code. Yeah, you can do it, but it's a waste of time. First, it's difficult. And secondly, there's a much more elegant solution. And that is you treat discharge as a state variable. So how do you do that? You see here that the fast flow, the slow flow and the fast flow, that they both end up in this, what I call a routing reservoir or the streamflow reservoir. So the sum of those two ends up in this new reservoir. Think about it as a swimming pool, that at the start of your simulation, the swimming pool is empty. The swimming pool has an infinite capacity, can never overflow. There is no flow out of the swimming pool. There is no evaporation. You see, there are no fluxes out of this. There's only water coming in that swimming pool. And that means that if I initialize that swimming pool at 0 at the start of simulation, and then I check what is its level at day 1, that the difference between what it was yesterday, the level of the swimming pool, and the level it is today, that difference, that is the amount of stream flow that went into your swimming pool between yesterday and today. Meaning, after you have your ODE solver solve for all the X values as function of time, so the amount of water in this reservoir, that reservoir, that reservoir, that reservoir, that one, and this one, after you have all those X values solved by the ODE solver, then there is one more step. You take the difference in this last state variable, xm, between yesterday and today, and that difference is Q. Now keep that in mind, because that is exactly what is written here, that Q in the interval of t is the mth value of x. X had m values, right? M state variables, between t and t minus 1. That difference divided by t and t minus 1, which is usually a day or an hour. So you just take the difference in the state of that last reservoir. And why do we do this again? Instead of having Q as an output of your model, which we still have, it is an output now, but it's now a state variable. It's now part of the state space. Now,
So just to be clear, Jasper, what you're doing is adding one more tank on the end, and that's just an integrating reservoir.
Yes,
It's integrating over time from 0 to whatever. Yep.
yes.
Okay, thanks.
So so now we have this additional state variable. Yeah. So let's go back to our equation because we want to get the sensitivities. Now, the mathematics literature has done this for us. This is called forward sensitivity analysis. And so you can differentiate your ODE system with respect to parameter J. So if you look at our original equation, that was this equation, right? And that dx dt in front, if you differentiate the left and the right-hand side, then we get this form. And now you can evaluate this right-hand side by applying the chain rule. So you can write out this part of your equation and you can write it as follows. This part and this part. Okay? This is just pure mathematics. And now you end up with a matrix here, this part. We call this the Jacobian of the system dynamics F with respect to the state. So let's go back. F is our system dynamics. It's the dx dt. So at each time, think about the car traveling. At each time, we can compute the velocity of the car, the speed of the car. Okay, that's our, so imagine you have an equation where you enter time and the current state, that is the location of the car. If we are in one dimension, then we have an x coordinate. The car is traveling. We start at x is 0. We know the velocity at time 0. Then we know where the car is at x is 1. Then at x is 1, we recompute the velocity of the car. And then we compute where the car is at x is 2. Now we take intervals, integration intervals of 1, right? The ODE solver can take smaller steps based on how much the velocity is changing. But F is the system dynamics. It returns the velocities, the dx dt's. And so this is the Jacobian of your system dynamics, dx dt with respect to x. So if I change the first state variable a little bit, how much do the dx dt's change in response to that? Same for the second, the same for the third. This is a matrix of m by m. We have m state variables. So this is an m by m matrix. And the key now is that for all these hydrological models, you can compute this analytically. You can derive these equations analytically. That's not difficult. I did it myself first, and now ChatGPT does it. I have a C++ code with the solver. It's like 600 lines of code, so no big deal. You upload it, you tell the ChatGPT, hey, I don't want 6 reservoirs, I want 9 reservoirs. You just in words, you say what you want, and the code is spit out, including how to put this matrix together. Now, so this one analytically, and I'll show you next an example. And then we still have the second part, this one. This is the Jacobian of the system dynamics with respect to the parameters. So how much do the dx dt's change when I change a parameter? That's a matrix of m states by d parameters. D parameters, and we have m states x. And this one, you can also compute analytically. Once you know the equations of your hydrological model, you can compute both of these analytically, just filling in numbers, essentially. Now, once you have this one and this one, you can write your original equation in this form. And yeah, that's all okay. And
May I ask
now
a question before you go on, Jasper? May I ask a question before you
yeah,
go
of
on?
course. Yeah, go ahead. Yeah.
So, as I'm seeing this, I'm reminded of work many, many years ago on data assimilation, which you also did, in which in classic data assimilation, they only assimilate into the states. Yeah. and they assume the parameters are known. And you can always think of parameter estimation as a kind of data assimilation, but where you're estimating the parameters and you're assuming the parameters are constant or fixed. Whereas in classic data assimilation, the parameters are varying with time. And what you're doing is a kind of time step by time step adjustment or correction to the state variables. It sounds to me that there's a very strong mathematical thing going on here, which could in principle be used to help design data assimilation procedures where you're interested in both estimating states or correcting states and correcting parameters. Just curious if you've given that any thought yet or what you think about that. Yeah.
No, that's an excellent suggestion. I haven't thought about it yet in that context, but we compute the JF and those two matrices, we compute that at every single time. It's a byproduct of the OD solver, and
Right.
you can actually, yeah, you should be able, that's the local sensitivity at that point. So you should be able to use that to distribute your state update into the state space and into the parameter space based on those local sensitivities. Yes.
Right. And you could put some kind of weighting and decide
Yeah.
which one's more. But anyway, just a thought. Keep going. Thanks.
Yeah. So, yeah, that's interesting. So now I'm not going to skip yet to Appendix B, but because that shows you how you can compute these for models. But let's continue. So now we're back to this equation. And now we have J of F, JF of theta, and I also see the time. So I want to spend some time on the interface. So this part of the equation, we coin S now, okay? And so this S is a matrix of M by D. So after I compute the right-hand side, I have this part, and that's the change in X, the state, with respect to theta 1, the change in the state with respect to theta 2. Now, the state is a vector, vertical vector. So this entry here is the same as this first column. This entry is second column. So this is an M by D matrix. So essentially, we write this equation as follows. We write it at this equation. So the change in all those variables we call a sensitivity state now, which are different than your X values. These are new state variables. That's just this part of the system. That's only the sensitivity part. Those are added to our system, and we call those individual the sensitivity states. So you can write that equation as follows. And then we have our states, our normal system, where again, this is the change, dx dt. This is our state. This is the change in state, change in time. And we add to that the factorized form of this, because this is a vertical vector, and we add to that a factorized form of our sensitivity states. So this becomes a really long vector, and these are the equations we solve. So now what you're going to have is, if you combine this and all those sensitivity states, you have a matrix or a vector that has m times d plus 1 entries. It's a vertical vector. Instead of having only m entries, now we get an additional d plus 1 times m negative 1 additional elements on top of x. And this, a solver can solve really quickly. Okay, now then we're almost there. If we can solve those sensitivity states, now the key, remember, x is our discharge. X was our last state variable, xm. That was the last state at the end of the chain. S are the sensitivity states. So we know the sensitivities now with respect to x, with respect to q, but what we need to know is the sensitivity with respect to discharge. We now know the sensitivity with respect to x1, x2, x3, x4, x5, xm. And so to get the sensitivity with respect to discharge, we need to take the difference between xm today and xm yesterday. And that's what you can do by taking the solution of this and subtracting its solution of yesterday, and then entry m, right? This is a matrix, it's factorized form, so you end up in this form. And that is immediately then how much is the discharge change with respect to parameter j, and that's your Jacobian entry. And given the time, this is the difficult part, I understand. So this requires you to study a little bit, but essentially all this is called forward sensitivity analysis. I don't like that word, to be honest. It's really very confusing because most people with sensitivity analysis, they think about something else. But this is within the ODE literature. This is not this in the context of hydrology, but this methodology is now I'm not saying standard, but is well known. The key is to treat discharge as a state variable x. That's the key. If you don't do that, this cannot work. So the key insight is to know that this exists, and the second key insight is that you need to bring q as a state variable. Then it works. Otherwise, if you don't get that first step of treating q as a state variable, then you can't implement this. Now, loss sensitivity vector, we now have the Jacobian. The ODE solver now will give us the Jacobian. We only need that second vector, loss sensitivity. Now here are the loss functions, and here is the loss sensitivity vector. It's just differentiating each loss function with respect to q. That's easy to do, even for KGE, NSE, Huber robust loss, and the flow duration curve, a 2024 paper I published where I show how you can use information theory to derive quasi-likelihood type of scoring rules, and including the flow duration curve loss. Now, example here, the rest is in the appendix. If you have the NSE and you want to differentiate this one with respect to q, then here it is. KG, if you want to differentiate KG with respect to q, I see your hand, Jonathan, 1 second, then you can do that as well. It's just mathematics here. Let me see. Jonathan, go ahead.
Yeah, I don't know why I'm asking you now because I could have asked you anytime we talked about it before, but you turning the discharge into a state variable, it's like when you solve a conceptual model like this, we're basically doing a finite volume method, which each one of like the conceptual reservoirs are just like finite volumes. But would that also work with like finite difference or like finite element, the forward sensitivity analysis? Have you seen that in the literature?
Yes, it depends on your differential equation. If it's a partial differential equation or an ordinary differential equation.
It just has to be ordinary. Okay.
Yeah.
Yeah.
But for instance, for Richard's equation or so, we can write an implementation that also works for Richard's equation. You just have to linearize, but yeah.
Yeah, okay. That makes sense.
Okay, so I'm running out. I don't know how long but okay, so assume now that I'll show you the implementation next, but now something else. Because this first paper is just a theory, and it has nothing to do with that SAGE part I'm going to describe now, because ultimately the idea is to use this to run a hydrological model so that we can train for any region in the world using all data available. Okay, so one more thing, talking about training, we now have the gradient for free, essentially, for any differentiable loss function you like to use. Now we do training, but what do we train? We have the constrained hydrological parameter space, because hydrological parameters have bounds, right? Porosity cannot become negative, cannot exceed 1, so they're bounded. So how do you do that in training? Now, what I do is I first transform the hydrological parameter values to the unit cube. And then you can use a logarithmic transformation. This is what neural networks do all the time, right? The signal between 0 and 1, they go between negative infinity, infinity, or the other way around. So you can transform the unit cube to the unconstrained space using log transformation. So I thought it's best to train in the unconstrained space. You train in this space, then you transform back to the unit cube, and then you calculate what the actual parameter values are. But after trying different things, I train all my models in the unit cube. That I found to be most efficient, even though you have bounds. Going to an unconstrained space is not ideal because it has other problems associated with it. That when you're approaching the upper bound, that it takes large steps ultimately to get really to 1, because your slope gets almost 0. So I train all my models in the unit cube, and I indicate that by using an underline under my parameter values. You see, theta underline means we're in the unit cube. These are the original parameter values. Then this is the parameter values on the unit cube. And the transformed, I use the var theta symbol, but I'm not using this. I'm using the unit cube, okay? Because you need to keep all that in mind because you have transformations. Those transformations you need to account for during training because you train on the unit cube, but you're interested in the hydrological parameter values that are unnormalized. So that transformation, that's a Jacobian. You need to take that in consideration. And so here it's explained that we can have a Jacobian of discharge with respect to our hydrological parameter values, but we can also have a Jacobian of discharge with respect to our unnormalized hydrologic parameter values. That's almost the same Jacobian, except they differ with that transformation. So you can compute one from the other if you account for that transformation. Now, okay, let me quickly show you. Then one more thing, numerical differentiation. Typically, when we do numerical differentiation, here's an example. This is a function. And suppose I want to know what the derivative is at this point. Then you would say, perturb x a little positive, perturb x a little negative, see what the change is in the function value, and then you have your line. That's exactly this brownish line here. That's our derivative. That's our tangent. So if you make x small enough, that perturbation, you make that small enough, in Leibniz notation, that h goes to 0, like the limit of h going to 0, high school, gives us the derivative. But in practice, we don't know what type of increment to use. Okay? So you can use all kind of different increments. And you see in this example, you get very different derivatives. If I use this increment h7, this one, then I get this as my approximation, which is still a little different than this. So what increment to use? Now, if you do numerical differentiation and you really want to get it right, then there are methods that do this adaptively for each parameter. But you can imagine that's a lot of additional time, okay, if you want to do this. Now, my point is, in hydrology, people tend to use a fixed increment, but what increment to use? You can use an adaptive increment. Now, automatic differentiation, I just want to show you here, when you do the Jacobian entries here, you see your numerical versus analytic, and they're a perfect match. That's essentially what this first paper does. It just shows that in this case, 4 different models, analytic Jacobian is the line, the squares are the numerical Jacobian, which again takes much more time to compute. Here you see comparison, the speedups, analytic versus numerical Jacobian, and that's for 1 year of data only. Here is a comparison, and I'm sorry I'm rushing now given the time because I want to show you a computer implementation of all this, what this is leading to. That is called SAGE, Sensitivity Aware Gradient Estimation. So this is an executable.
Jasper, if you have the time, don't worry about it so much.
Okay.
We've only gone an hour. We often go an hour and a half or longer. So
okay. So here I compare, because people may not believe that the analytic and the numeric gradient are the same. And here I just show that this is for the Sacramento model. For each parameter, I just plug in parameter values. I compute the analytic gradient and the numeric gradient for the sum of absolute residuals, for an sum of squared residuals, for an NSE, for a KGE, for that Huber robust estimator, and for that flow duration curve loss. And you see they're identical, except the analytic is instant and the numeric requires you to do all kind of additional model simulations. And if you use an adaptive scheme, that takes a lot more time. Here, a gradient comparison, you see numeric versus analytic, perfect match. And here the speed up for the gradient, this is only with 1 year of data, okay? This gets much worse when you use 10, 20, 30 years of data. And here is a comparison, no, same stuff. Let me see here. What do I do here? CPU time in seconds for computing the gradient factor of those 4 models. Now here are the models. This is the CPU time, how long it takes to compute the gradient factor. And this is the time it takes to do that with automatic differentiation. You see the difference? This is 1 year of daily data. So this is the CPU time. This is with MATLAB, okay? Maybe you know better ways of doing automatic differentiation, but using my ODE solver with automatic differentiation takes this amount of time. It's crazy, right? So here are no, that's not so. Let me, oh yeah, here. So here I do gradient descent now. I start at exactly 25 points or so. Each point is a different color, and I do analytic gradient versus numerical gradient. And you see the trajectories are identical. The results are almost identical because I compute the numerical gradient using that adaptive numerical differentiation scheme, meaning it's really accurate, but it takes a lot of effort. Here are the parameter trajectories, and you see now with a low complex hydrological model that essentially almost all trials converge to more or less the same solution. Because we use an ODE solver, the surface is smooth, we no longer have the issue of local minima that much. There's still a few, but we don't have millions of local minima because the numerical solution of the ODE solver gives a smooth surface. You see that the trials identify approximately for each of the parameters the same area. Now, if you have more parameters, you start to see that there are different regions of attraction, okay? So they're not all converge to the same point when you have more parameters. You start to see that they end up in different parts of the parameter space.
Question, Jasper.
Yeah.
If you go back to that previous graph, what's the reason for this long burn-in period? Do you know?
A long burn-in period.
It takes a long time before the parameters start to, it takes like 40.
Ah. Yeah, that's a good question. I never actually.
It's learning something before, then it starts to very suddenly make a rapid change. But in the beginning, it's kind of like just sitting there.
Yeah. That's interesting. I never even thought about that. You're right. The first 30 iterations are essentially. Well, let me look at that. It's a good observation. Yeah. It's really weird. You would expect it immediately to move, right?
What is LM iteration?
Levenberg-Marquardt.
Okay. So that's the gradient-based optimizer, right?
Yeah, it uses the gradient of the ODE system, what we just discussed.
Yeah, but LM is learning a quadratic approximation. So maybe that's the time required to start getting a decent quadratic approximation.
So Yeah, let me look into that. It's interesting. Good point, Hoshin.
Okay.
So so here I try different loss functions. The point is you just change that loss sensitivity vector. You don't have to rerun the whole thing. And here you see 20 trials for the sum of absolute residuals, how they converge in terms of this is the loss value, not parameter value, just the value of the loss. So you see that they not all converge to the same final loss. And this is, which model is this? This is the Asian model, Xin and Yang. And so this has 15, 16 parameters. But you see for I think the NSE, they tend to identify, there's some small variations in here, but they all converge essentially to values of 0.9 here. KGE, it's a little bit more variation here. This is that Huber loss, there's some variation, and particularly in the flow duration curve loss, you see there's really variation, and that goes back to the magnitude of the gradient. The sum of squared residuals has by far the largest magnitude of the gradient. And the flow duration curve loss has a very small magnitude, which makes it much harder to search. Okay, and then here, taking the best parameter values, just comparing against data. This is hourly data. So that was just the first paper, okay? And that's just the theory part showing we can do this analytically much faster than automatic differentiation. Then I called Jonathan before. I said, Jonathan, that neural hydrology, I'm thinking to redo that with analytic gradients, and I think I need about 4 months or so. He said, you're crazy. No, he was quiet. There's no way. That's years and years of work. It's never going to work. But to be honest, once you have this implementation, it's really easy to scale this. So that's what we did. And that's that second paper here, where I implement this analytic gradient, but now for US training. Okay, so I'll show you what the result is of that. Is this package, you can download this, an executable, you can install it for Mac and for Windows, and then you will see this screen here. And I added some new regions. So you not only have United States, you can choose Switzerland, Sweden, New Zealand, Luxembourg, India, Great Britain, Germany, Finland, France, Colombia, Chile, Brazil, and Australia. So let's just take France or so. And you see here that if you probably, when you download it, this executable, you don't have the data. So you just push this button and it will take the data from Zenodo or so, or whatever where it sits. It will take it, install it on your machine, and then it will say present. So the daily data is present now, and the couch metadata is present now. So I don't have to download it. Okay, so pick any region, you press.
Just to be clear, Jasper, you're now talking about fitting a model, a conceptual model, but to multiple catchments simultaneously.
Yes.
As in the standard approach.
Yeah.
And you're learning a pedotransfer function or a mapping from static. You might want to make sure that's clear before.
Yeah. Oh, yeah. Okay. Yeah, I was going to get to that. So basically, you're right. So we're now taking the theory for a single model, getting the gradients for essentially almost free, and now applying that to train that model for many different watersheds using the large sample data that's available, that CAMELS data. And the way this is done is through a neural network. Okay, so I'll get to that network after I select the model here, I think. Let's see here. Here's a network now. So these are, let me show the attributes. So this is for France, the data set France, and they have all these catchment attributes, static attributes, a whole list, 899, okay? And the ones that are, these ones means that for some watersheds they're reported, but not for all watersheds. In France, we have how many basins? Let me do this first. We have 654 basins. Let me show you. I'm dividing the basins now in training and evaluation basins. I'll give you more and more details along the way, okay? So here are now the training basins. I have 500 of them. Here they are, 500. And the rest, 154, are the evaluation basins. You see, 154. And this is the basin ID. You see the ID numbers here? Now, here is the map of France. You see the training basins and the evaluation basins. And then here are the zones, the hydroclimatic zones. That this is automatic classification, okay? I think I provide aridity and something else as input. So it identifies 4 zones, and these are the training and evaluation basins. Okay, so now we have that. Then for each of these basins, we have
you're doing stratified sampling to preserve the same fractions in every zone, correct?
Not
No.
Not in this implementation. No, there's
Okay.
others that yes do that, but
Okay.
not in this here. You can try different things here. So,
Okay.
but yes, that's easy to add. Yeah. So now we have the attributes for each basin. And now we use a network to turn those attributes with the transfer function into normalized hydrologic parameter values between 0 and 1. So for each catchment, we have all these attributes. And then this network, you feed them in, and it predicts what the hydrologic parameter values are in normalized space for that basin. That's how it works. But now the key is, what are the weights and biases that we use here, right? Because that mapping between catchment attributes and parameter values needs to be accurate for the discharge to make any sense when we compare it to actual measured discharge for each basin. So we need to train this network. So instead of training directly on the normalized hydrologic parameter values, we're now going to train on the weights and biases of the network. Now, we wrote a paper about that, and that's this second paper, sensitivity or gradient estimation for rapid continental scale. And here I work out the mathematics, starting again with the pointwise loss, the neural network, taking the catchment attributes, turning that into normalized hydrologic parameter values. These are the catchment attributes. Then once I have the normalized hydrologic parameter values, I take the max and the min of the parameters to turn that into the actual hydrologic parameter values. And now I have, for each watershed, I have a total loss. Then I have K watersheds, and that gives me the CONUS loss. I call it CONUS here. I will call it SAGE because we can do many different regions. This implies that we only focus on the United States. Now, if you work out the chain rule now, we want to know how that total loss for an individual basin depends on the weights and biases. You can write out that entire chain rule, and you get this link where you have your loss sensitivity vector, you have your Jacobian, this Jacobian, and there are 2 more Jacobians that you need to take into account so that you're estimating weights and biases of the neural network, not the parameters of the model. You're estimating weights and biases of the neural network. So here the whole mathematics is written out. Okay, and then the architecture is explained here, and number of parameters, etc. So that's in the second paper. So now, let me take, most of you are familiar with HBV. Parameters of HBV, you can change the min and the max if you want. ODE solver, if you don't want the advanced mode. This is really for a more experienced user that don't mess up the ODEs. You don't have to touch them essentially. They're fine. Period. So now we need to talk about the data period. What are we going to use for evaluation? What are we going to use for training? Are we going to use manual dates where we have a training period start, training end, evaluation start, evaluation end? Or are we going to do a deterministic block? It's explained here what that is. Or are we going to do random, where we just divide the entire time series in training and evaluation? So they can alternate training day, evaluation day. This is daily data here, by the way. I'll show you hourly data as well in another run. But we're not used to this, right? This type of training evaluation. But that's possible. And rainfall block. This is something one of Hoshin's student is implementing. Maybe it's been done by others, but what do? We divide this record from 89 to 2008. That is about 20 years. For each year, for each watershed, we calculate the total precipitation. We rank that from high to low, and then the wettest water year goes in the training. The second wettest water year goes in the evaluation. The third wettest water year goes in the training. The fourth in the evaluation. So this is the idea essentially. Okay, that you can alternate, which is not going to happen. You can have 3 years next to each other that are all training, followed by 2, or you can have any combination. Okay, so this is now going to differ per watershed, because in one watershed, year 18 may be the wettest and year 15 the driest, whereas in another watershed it's totally different. So now we're going to have each watershed has its own evaluation and training period. Now let's do that. Meteo data, it's explained here what available products are, because some of these CAMELS products offer multiple temperature, multiple precipitation, multiple PET options. And here you can decide if you want to use Penman. Oh, it's okay, good. It wants Penman Montes. Okay. Basins we already stratified. Attributes, now you can decide which attributes you want to use. I just took a selection here. And again, this means that you can select them. That means that for some basins, those attributes are reporting a missing value or not a number. So network we have now, it says now that we're estimating about 1,400 weights and biases. Loss function, now here the loss function. You want to use the sum of absolute residuals, or you want to use generalized least squares, or you want to use the Ness-Sutcliffe, you want to use the Klinkhup efficiency. Let's use the KG for now. Training, Adam, you don't have to touch this typically. 500 iterations, learning rate, weight decay, clipping, diagnostics. Okay, so let me divide the basins one more time. So you're going to see our training and evaluation basins here. And so diagnostics allows you to tell the computer, okay, what do you want to see at the end and during training? Which basin and which period you want to show? Because keep in mind, we have training basins, evaluation basins, and we have a training period and an evaluation period. So you have 4 combinations. Training basin, training period, training basin, evaluation period, evaluation basin, training period, evaluation basin, evaluation period. So you can select here what you want to see. So I just say, show me the first 5 of the training basins, both periods, and the first 5 of the evaluation period, both. Now let me now compile the model, which is not needed in the executable, and now we're going to run. So I hope you can see this. And hopefully my computer doesn't crash. So this is daily data. So it's reading the daily data now. You can see that here. Now it's setting up the parallel pool. The good news is that this new computer has 16 cores, 32 threads, but it did crash this morning. An hour before my talk, the screen suddenly went black. So I told my wife, because she's been knowing the computer, what's going on the last week, and she almost got a... Okay, it's starting now. Here we go. So this is the KG, and here you see how the KG is now going as function of iteration. And this is the summation of 1 minus kg. We're trying to maximize the kg, but we're dealing with loss functions. So we want to minimize. So we take 1 minus kg, and then the summation over all those 500 training basins. And then we have the evaluation basins as well. Okay, and I show the performance for the evaluation basins over the evaluation period. So here, this is the training NSE, training KGE. This is your evaluation basins, evaluation period, NSE, KGE. So here you can see essentially, yeah, this runs really fast. Here you can see the iterations. Now they take 3 seconds for 650 basins, 3 seconds. So here you see the runtime. This is the runtime of the GUI. Let me show you the zones again. Trace, here you see parameter traces of the hydrological model. You see how they behave. We have 670 or 500 training basins, right? So you see the mean of those 500 or the median, and you see the 15, 70, 90% or so. Here is the variogram, where you can start to see how the parameters behave spatially. So this is the parameter FC, and you can see the spatial relationships that start to develop. This is the range that I included, because you see after a certain point, this is geostatistics, there are not too many data points, and you cannot really trust your variogram data. And you can change if you want an exponential function, you fit an exponential function here, or a Gaussian. Metrics. Let's look at the metrics here. So you can plot all these metrics. So even though we're training on the KG, here you see the KG, the mean KG. Okay, so again, we have all the bases, so we compute a mean. And here you see how it behaves during those 4 different scenarios. And you always expect the training to go up, but the other ones may not necessarily go up, right? And that's what you see at some point, that the training still improves, but the other periods go down a little bit. So far, so good. Training improves, training basins and evaluation basins improve. So you're learning something that generalizes. But now you see that the evaluation is, now let's look at the NSE, median NSE here. See, the training still goes up. But anyway, you can look at any of these loss functions. FTC, here the flow duration curve. For the selected basins here, you can look at the performance of the different periods measured and observed. So this looks pretty good. And now you can also look at other basins. So this is the evaluation basin, color change, evaluation period and train period here. So that's essentially what you can monitor. And if you're done, or your computer starts to explode and smoke, now we've done how many? 53 iterations so far. It keeps getting better. We're now at an NSE of 0.65, KG of 0.71 after 2 minutes, right? Not bad. Now you can just say, okay, I've had enough. I need to go for the dog walk, and you push stop Sage. And now the log should say that it stops. And now it is exporting all the results to a binary file. It's creating all these output plots. And then it's creating a PowerPoint file that should open up now with all the time series. And let me show you, it's actually quite nice. That new idea of the rainfall block split. Give it 1 second, because it's now writing to PowerPoint, and then it opens the PowerPoint. I can show you that. So, and then we'll do one more with hourly, and you'll see it takes a little longer, but still. Nah. So this is the results file you get from Sage. Model HBV, region is France, resolution is daily, training period, evaluation period, spin-up period, objective function, the type of splitting method, number of training basins, evaluation basins, the attributes you used, Meteo product, Precept product, PET, temp product, the FN architecture, all this stuff here. Here, this is then the summary for the 4 different scenarios, training basin, training split for the NSC, so the median NSC values here, KGE. Then here, how the performance per hydroclimatic zone. So this is hydroclimatic zone, and here are those 4 different scenarios again. So that you can see, in terms of France, we're actually doing, you see, you start to deteriorate a little bit here, which is maybe mountain. No, maybe not too bad. Anyway, it gives more insights. This is for the NSC, this is for the KGE. Then this is the parameter traces, right? We have, we're training the whole population. Point is, people working on doing this similar stuff, they're very familiar with these plots. I don't know if all of you are very familiar with these type of plots, but here you see how the parameters change over the map of France in this case. And I know it's hard to see, but training basins are in blue, evaluation basins are in orange. And the lighter the color, the lower the value. And they're all between 0 and 1, right? The parameters. So this can be used to see spatial patterns. It's like, for instance, here, for this parameter BRT, you see that you clearly said that the vast majority of France at its value are generally smaller here as well. K2, so here are the variogram function, I don't like this, but here are the time series plots. So here, this is training basin, and remember we do a rainfall split, meaning we have the entire period, and we have training years and evaluation years. So what you see here is the training years are in grayish. I hope you can see the colors. So this is all training, and this is a evaluation year. This is a training year again, right? Yeah, and this is evaluation. So I tried to use the different colors, but that's how it looks. And this is for different, those 5 watersheds we selected, the ones that we picked that we wanted to see. This is the 5th. And then here it's for evaluation basins, and the 5 we selected for the evaluation. And here are the flow duration curves for those watersheds. This is training, 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 evaluation, and then evaluation, training, and evaluation, evaluation. So that's essentially what Jonathan and I produced. So let me show you one for those the hardcore. We can do Germany. Germany has hourly data. So let's take HBV, fine, OD period. This is the German period. We use 2005 to 2021. And it's hourly data. And we have 1,256 watersheds. So hopefully my computer doesn't explode. So here again, the cage and the zones. So if you look at Germany, these are the hydroclimatic zones where I said I don't want more than 6 or 8, okay? This is what it came up with. And of course, this you can refine this. And then my home country, the Netherlands, but there's something missing here, a lake. So yeah, that's remarkable. But so for those that like German, by now, I think I've seen all the watersheds of the world, the ones of the camels, right? You see the most beautiful names. But here are the attributes for Germany. 97 different ones, and they've all been reported. So there's not ones that you can select. Now let's use a one layer network loss function. There's one loss function I haven't talked about. That's work that Hoshin's student did. That's called JKGE. And Jawad Mohammed has given a talk about it a few weeks ago. So that's implemented here as well. There are two implementations, but let me just go with the least squares or so. It works, but people are not familiar with that yet. But diagnostics, now let's see how long this takes. Now run. So it's reading the hourly data, 15 years or so. And Jonathan, you have the Google Drive stuff, right?
Yeah.
We can share that link, and it's an older version of this.
Yeah, I'll put it in the chat.
Okay. Okay. So okay, we still have some people listening. Good, good, good. And I saw some things in the chat. Let me respond to that. But I'm so during all this coding, I haven't really tested much. I only looked at the United States, but all these other regions, I just do a test run that everything works, and that's it, essentially. So obviously, there's so much to do.
Jasper, while we're waiting, could you maybe comment on what's involved in somebody putting in a different model than one?
Yeah, very good. So let's do a few iterations with this host, and that's really good. I forget that each time, but because then I can show it's already in the interface. I can pull it up, but now I can't because it's inactive.
That's fine. We can wait.
Here, so model here, it's inactive, but there is a user model option. I'll show that. Yeah. Let's see how long this should clean. So it's calculating now you see here the summary. It's 16 workers, and it's doing the first iteration. So 1,300 watersheds, 15 years of hourly data. What I remember, it should be around 50 seconds or so, one iteration. But that assumes, yeah, okay. Same stuff, 1,000 training basins, 256 evaluation bases. This is now, we use the least squares loss. This is the total for all the basins. And about 60 seconds for one iteration. Let's do one more iteration, then I'll stop it. And yeah, you see the same things, right? That these things improve. And you get all the statistics and the binary file. And there's a binary file written with all the results so that you can work with that yourself. That you don't have
Jasper, on this screen, I noticed that like on the bottom left, there's that JKG on the bottom there. Yeah. That was there before as well when we weren't calculating the JKG. Is that supposed to be like that?
Yeah, this will show up when I use that JKG loss function.
Mhm. But so is this the CDF though?
Yeah.
Okay, I see.
So here you see the iterations again, and let me stop this now. So how long did it take? 60, 68 seconds. Let me stop it, and then I can show you the user model.
Jasper,
Yeah.
we're minimizing on the area under the CDF, correct?
No.
No?
In this run, we are minimizing the loss function here. What is it? The generalized least square. So just the,
Oh, right. Okay.
yeah.
But what you're hoping is that the area under the loss, under the CDF becomes as small as possible. I think that's, you also
Yeah, so that,
care
yeah.
about that. Yeah.
Yeah, so that's that integrated basin loss score that
Right.
Jonathan and I proposed. That's actually listed here, what the value is and how it behaves.
Okay.
But that I haven't implemented yet as a loss function,
Okay.
so that you can minimize that directly. Let me check here. Iterations, log. Okay. So it's making the figures now, and then you get an idea what hourly data is in terms of it's much more informative, I think. It tells you a lot about the routing, whether routing is going okay, because the response is so much faster, right? Whether it's an hour or a day, it's a big difference, that the peaks and all that. So there's still a lot to learn, but obviously hourly data, the data set is much larger. So let me wait. It's creating the figures now, still doing some post-processing. Let me check here. Yeah. It's doing some post-processing now. And yeah, so the next step is a user model. So if you go here, now it's doing post-processing. I actually can show it. Oh no, it's still inactive. If you want to work with your own model, you can. You know what? I'll just open it up here. So there's a user model list. So this is the program that you can download from the Google Drive. And if you have a Mac, then you have your Mac program. If you click on it, you see exactly what I see. Then here, if you place this user model next to your executable, then you get this directory with files. And here it's explained how you can build your own user model. I'll open it in, I still need to install Visual Basic and all that. Oh. So here is a user model core. It will tell you what you should change and what you shouldn't change. Okay? So this part you can adjust, which it's really straightforward. It's really not difficult. This you change with your parameters. So it tells you exactly here, and if you feed this to ChatGPT or some other, it will be able to do what you asked for. And so I'm considering writing a separate paper about that, but at the same time, I like to move on to do other stuff. But you have to change this file. AI can do that for you, and you have to change this file here. So this is a file where you, oh, now let's first let Germany do its stuff. So these are the German results after 2 iterations, but you get an idea of what that data means. You see here how hourly data looks? So much denser. It's okay, good. Here it is. So this is for Germany now. Again, this was only 2 iterations, right? So this is not very meaningful, but you see with the hourly data so much denser. So it's beautiful, the hourly data. But anyway, okay. So going back to the user model. So there are only 2 things. Here is your user model template. The template implements the GR4J model. I can make another template with another model, but it just gives a template of one of the models. And it tells you exactly which pieces you should change. And based on this template, like don't change the actual integration method, the numerical solver. Okay, there's no need to do that, you only have to change certain parts. And here at the end, here is your code. This is the part you write yourself. And again, this is what AI will do for you. So with Mohammed, you know what? Hopefully he can set up a case study where he's working on this now, where he takes this and that he's able to implement it. And I think that could be a nice paper in principle because it shows that there's active ways of using AI. I sometimes feel that people are a little scared talking about it, how I use it. But here in large part, this is just all, once you train it, it knows how to do that fairly easily. So based on this template, and then here there's another file where, let me show, where you specify the the parameter ranges. Yeah, here. So you just define your parameters here. Now, if you do that, then we go here, you select user model. This shows up now. And these are the parameters of the user model, and they're listed here. So the user only needs to change this block, and they need to change the ODE function here, and that's essentially it. So I can, let me try. Let me show you. Again, I haven't done this for months, okay? Because I haven't worked on the actual models for a month, but here, let me upload this. Here we go, SAGE hydrology, software, user model. Where is it? Yeah, here, okay. I like to change the present C code, C++, doesn't matter, code, and use another type of hydrologic model. Can you help me? I'm just doing this. I normally don't ask, can you help me? But let's just do that, see what he says. Another type? No, just another hydrologic model. Absolutely. Oh, he's giving me a compliment. This is already set up nicely. The key is that, yeah, exactly. So it will tell you exactly how to do it. And can you derive the matrices for the forward sensitivity analysis for if I specify model specifics? See, can I? Okay, here. Yes, definitely. Specify the model as. Now, that's exactly what's done. Then I can derive. See that?
So, general comment, Jasper. In principle, this doesn't have to be a mass conservative conceptual rainfall runoff model. It could be any model which has a dynamical state space structure, correct?
Yes.
So in principle, a person could treat this, they could use an LSTM with 5 nodes as a head layer, as the hydrological model, and use your neural network to estimate the parameters. And therefore, you could partition the estimation process into a local LSTM model and a global parameter specification model for the LSTM, as an example.
Yes. Yes.
Okay. So yeah. Okay. Because currently when people do it, they don't separate out those two parts. The LSTM is usually a global model, And so the part which is learning the regionalization and the part which is learning the local dynamics are essentially intermeshed together. You can't separate them out. But doing it using this package now allows you to separate out those two parts if that's something you're interested in. Yeah.
Yeah.
You
Yeah.
know what might be interesting in the future? I can imagine, because now you have AI to help you, I could imagine that instead of giving it a C++ model code, you can actually give it a directed graph image of the model you want with statements about the system architecture, the process parameterization equations, and so on and so forth. And it could actually write the code for you and then do all of this
Let's try it,
automatically.
Ocean. Let's try this. So let me upload. Let me see here. Docs. Let me upload. Let's do HiMod. No, okay. Let's just try because it's seen those, but let me try H model or so. I'm uploading this. Can you write this model in C++ ODE from following the C++ code I just shared? I can tell you that he can do this. So let me show you what that is. That file here is just this file.
Okay.
Just a PDF, and everything is specified here. I already did. So this is going to be a piece of cake, but he can just do it based on if you make a drawing of this and it will already be able to do it. Okay, here we go.
The reason I'm mentioning this is because the next step is actually to have the LLM generate hypotheses about the model architecture, and then have it generate the code, do all of the thing. This is what I was going to talk about in class next semester. So once you have this framework, there's a huge amount of leverage you can build on this to accelerate the model development process.
Yeah, here it is.
One other thing you can do is just describe to ChatGPT the perceptual model that you want.
Exactly. Yeah.
So
Well,
here
you
it
need
is.
to give it a certain amount of information because otherwise it has to make assumptions.
Right.
And have it ask you back. If it's not quite clear what assumptions you wanted to make, have it ask you back, right?
Right.
So you see here those equations. These are all these simple differential, how do you call the derivative equations? The
Cool.
derivative, you see them all appear here, and then it just fills the matrix, the Jacobian of the system dynamics with respect to X, Jacobian of system with respect to theta. It just fills each of these entries. Here it is. That's it.
That's very cool.
So yeah, I trained it, but I haven't done this now for a few months because I just, working on my original idea was to use this to generate new hypotheses. So I actually,
Right.
you don't see this, but here the models, I actually have new here, new tree, and I have here a C++ model which is way more complex. I started with 20 state variables, 30 parameters, but then I thought, okay, let's slow down. This is from a few months ago. I was like, okay, let's slow down because that is an infinite space, right? I said, I need more structure here. Let's just focus, let that go. But here, following exactly that template, and I also created very different models based on other literature. It doesn't have to be this type of bucket model.
Sure.
You can have very different type of models, and it all fits within this framework. Yeah. Hey, Jonathan, the fact that it runs 1,300 watersheds in under a minute with hourly data, 15 years, right?
Mm-hmm.
Like automatic differentiation, that would need hours or not?
Probably. So of the things that there are probably ways to speed up the training with automatic differentiation. So that's one thing that like we were kind of talking about with some of the different people a couple of weeks ago, Jasper, is like with Daniel at Colorado School of Mines. Well, one of the reasons it's so slow is because you have to rerun the warm-up period at every time step. So if you're running an hourly model and you want 6 months of warm-up period, you got to run 6 months worth of hourly just to make 1 hour's worth of prediction. Well, that's not absolutely required for training a model. So that's what like there's a training strategy that we're working on to just have a continuous state, which that'll speed up significantly. So, but to answer your question, yes, but not all of that is required.
Okay, but because there's a few other things. So I'm writing that software paper now. I can show you, which is just
Yeah.
the graphical user interface. So that's the last paper in the series where I just describe, I go over the individual tabs, what you can do, all that stuff, right? So while I am communicating with ChatGPT yesterday, it suddenly gives a synopsis of my work and saying, Jasper, if I were you, I would present it this way. And it knows me pretty well by now. It just from the synopsis, I see a level of understanding in there and a depth of knowledge that I'm like, so what I've seen over the time I've been using this unbelievable growth, that it is much more, it seems to be much more than just a dictionary. It's synthesizing things, putting things together that, and going to the conferences, this is all nice machinery, but I'm very worried in terms, not for myself. For myself, it is great times, but just in general, the education, the research, everything that we're doing, that like what Hoshin is saying, I think we should think big because all these little ideas are just not that meaningful, I think. They're important academically, but we need to think bigger, I think, if we really want to do something that is that sticks. Because also these AI companies, what they can do, it's just unbelievable, right? We cannot compete with them. So all I try to do is show, hey, if we go back to academics, mathematics, we can do this much, much, much faster. And that's all I essentially wanted to show. Because that speed offers opportunities. But in terms of competing with AI companies, it's just unbelievable where this is heading. Yeah, what it can do for you. Everything like I showed and Ocean and others just suggested, it's all possible essentially. So it's very exciting, but at the same time, yeah, we're not leading anymore essentially. So
Joe's got his hand up.
Yeah, I'm curious. It looks like most of the stuff is in MATLAB, but presumably because we have the function and the analytical gradients, we can have like a custom torch layer or something built in Python as well that would be useful for these hybrid models that like Chopin and others are creating. Have you guys looked into doing that?
a good point. There's a number of things I always forget to mention. That's one of them. Let me show you one thing. There is this button here, export script. Let me do it. I save. And let me open it in MATLAB so that you can actually see how simple it is. Open. So now we use the interface. This is what the interface essentially creates for you. But if you look at the actual code, this is the actual code. And let me open something that looks nicer so that you can see here, this is the MATLAB. If you were to run what I just showed from MATLAB directly, then here you specify the root. You don't have to touch this typically. Which region? Now, you can clean this up a little bit. Which model you want to use, you don't have to touch this. So you can just specify the model here. And then the basins, how many total basins, how many training, how many evaluation, and how do you want to do that sample split? Here, the period of training. Here's some settings for your meteorological data, your et cetera, et cetera, et cetera. How many, your loss function, number 1, 2, 3, 4, 5, 6. This is for the JKGE. What's the window size, et cetera, et cetera. Transfer function. So, and then here, this is the code. Here you compile the model. Here you read the attributes. Here you sample the basins. Your ODE settings you read. Here you do the split of your train eval period. Here you read the meteorological data. Here you read the discharge data. Here you prepare the statistics for the NSE, KG, and some others. Here you read the model parameters. Here you initialize the network. Here you set up the parallelization. Here you initialize the descent method. And here you initialize some other arguments. And then here's your loop. This is your neural network predicting the normalized hydrologic parameter values. This is your forward run where you run for each of the watersheds those normalized values. Here you compute the performance metrics. And here you do the updates for plotting of the trace plots. So you can leave this out if you don't want trace plots. And here you compute your gradient or your update your gradient. Sorry, here you compute your gradient based on the gradient that comes in from the camel's run, and you combine that with the Jacobian of the network to get the new updated, the changing gradient, and here you then do the descent step to the new parameter values, where the new weights are old weights plus this thing.
So I know that Jonathan uses Python. I'm just wondering, has like a custom layer been implemented in Python so you can just add HBV as a neural network layer itself, instead of doing like a linear layer or whatever?
Yeah, maybe. So this is all very easy to code. So for people to understand, why is this so fast? Because I'm running in C++. The actual model codes, let me show you that. If this, what I just showed you here, this camels, the only thing it's doing, it's calling this CRR model. And here you see the different model calls. And each of these calls is a C++ function. And that runs the model, returns the discharge and the Jacobian. So this is super fast. Even though for each of these models, I also offer a MATLAB implementation. Let me open it. Here you see, you can say model code. If you do 1 here, you get Runge, Kuta, and implementation MATLAB, ODE MATLAB, explicit Euler in MATLAB, and here number 4 is the ODE implementation. So here are the cases. Case 1 is Runge, Kuta, and MATLAB. Here you see the MATLAB code. Here is the ODE in MATLAB. Here's the ODE call. Then the explicit Euler solution is here. And the last one is the C++ solution. So I always pick this one. But all those 4 different implementations are all in this code. And if you want to add the Python, but you can add all this stuff here, Joe. All this stuff you can code in Python easily. It's really basic functions essentially. If you want to run this, and then the interface itself, this is the interface itself, which is like already 25,000 lines of code. Yeah, that you can also code in another language. But I'll share all the source code. I'll upload it in the next 2 weeks or so on GitHub, so you can do with it whatever you want. That C++ code of the individual models, I took computational efficiency at heart, so I wanted to write codes that are very efficient, but not at all costs. So I'm pretty sure that we can still make them faster. Most of the time in these hydrological models is spent on reading the data. The actual model run, that time is minimal, even with hourly data. It's the initialization, porting the data, precipitation, temperature, all that data to the model is a relatively large part compared to computing the discharge, all these other things.
And I'm also wondering, would dynamic parameters cause a lot of issues with the analytical gradients? Or are those possible as well?
No, I don't think so. But for me, I have a hard time with that concept.
Mm.
If the goal is to get the best performance metrics, then that's an option you can pursue. But for me, I like to try other things first before I arrive at, like, one of the things I was thinking about, we can create a multi-model, which is a combination of all the different models, like a BMA type idea. And we train all these models simultaneously so that the mean or the median prediction gives the best performance, to see how close we're getting to, the AI models, the LSTMs.
Yeah.
Like, I
Actually,
like to do it.
Chopin
Yeah.
did that in his paper. He has like just 16 HBVs, and he shows that it's basically the same as um, gives you basically the same performance as having the dynamic parameters. Yeah.
Yeah. So I like to explore those. I did data assimilation as well, because you can implement. So I wrote the data assimilation implementation of each of these C++ codes. And of course, with an ensemble Camel filter, I think I have it here somewhere. Yeah, HIML 2. So this is with the Camel filter added to it. Um, yeah, with data assimilation. So here you can see, so that's another way. If you care about, improving, you can do state estimation on top. This is mathematically really interesting, because now when you do the sensitivity states, you're refining your other state variables. You're changing them from a forecast to an analysis state in the state update step. And that breaks the mass conservation, which is not probably that important, but it breaks the relationship between the sensitivity states and the state variables. So I worked out that math, but that works. Another thing I was thinking about is to use that sandwich work. Here, that sandwich paper, this one, to add that and get probabilistic estimates, because there's still an advantage if we if we define the uncertainty in a more proper way, more properly. If we take the median or the mean, that should give a further performance enhancement. So I think there's still different things we can do without using time variant parameters and get close to the performance of an LSTM.
The direction that interests me is going in the direction of regionalization. In other words, I'm interested in minimum description length approaches, and that might suggest different architectures for different parts of the country. But I just, and then you could use things like neuroevolution of augmenting topologies, the neat procedure to evolve different hypotheses and have those hypotheses tied to static attributes or information. But I just wanted to mention Dan has a couple of questions in the
Okay. Oh, sorry, Dan.
meeting chat. Yeah.
Let me see. What is the chat? Gosh.
Oh, why don't you just read your questions,
Sure,
Dan?
sure.
Sorry, Dan.
That's okay. No, I just put them up a moment ago. I guess my interpretation is you showed that between the analytical and numerical approaches, the parameters came out identical. So my first intuition would be that, well, that should mean that when you go to regionalization, that the results should be identical as well. And I just wondered if that was actually tested, because anytime I've had an intuition like that and I've tried something, I'm always surprised, especially things like ranks. And then the other one was more specific about the FDC loss. Just wondering what how much of the tail was captured in that evaluation, like the quantile levels or the I imagine they're equally spaced, equal quantiles, but how much of the tail is captured, because that I think drives a lot of that score.
Okay. Yeah, thanks. Those are definitely good questions. Question one. So numeric versus analytic. You should get the exact same results, but that is not the case in the literature. And what I'm trying to say is that when I implement numerical differentiation, I use the adaptive scheme, which decides what is the perturbation I should use, so that the numerical derivative is as close as possible to the true derivative. So there's a lot of theory on that essentially. But I know, so that's an adaptive scheme, which is computationally expensive because you have to try many different perturbations, rerun the model. In hydrology, I know that people don't use that. They just use fixed intervals. They use a 1% perturbation, right? Now, based on the fact that people use a fixed perturbation almost, all over, I can tell you that the results will not be the same. Only if you use an accurate numerical differentiation scheme will you see that the two are identical. But people don't use accurate. So you'll get very different results, analytic versus numerical, or not necessarily the same. Let's put it that way. Because the adaptive schemes, I don't think people know they exist, maybe that, but also they're just more demanding. They require many different forward runs. And then for each parameter, you need to decide what the right perturbation is. It's really interesting mathematical theory, by the way. If you look how that's done. So that's one. And then two, now I forgot your question. Two was related to
The
FTC
evaluation using the float, yeah, FTC loss.
oh yeah. So that flow duration curve score is essentially something similar to that interbasin score. It's just like what I remember, it's just if you have the measured flow duration curve, or I should maybe do this way. If you have the measured flow duration curve and you have the simulated flow duration, it's essentially the area between. And that you want to minimize. So it's not a specific quantile, it's just the overall area in between.
Yeah, I guess my question is, how far do you go in the tails of the FTC?
Okay.
Because it's really sensitive at the ends.
Yeah. No, how far do I go? I think I go to the first observation. So if you have a time series of n so the answer is n. So the extreme tail, or the first data point essentially.
So it's going to depend on how much data is in each portion of the flow duration curve. If you have a lot more data, it'll tend to emphasize it more. Yeah.
And so I've never done runs with that flow duration curve score loss. So in this case, if you go to the loss functions here, I have never selected this one actually. It's implemented, but now the JKGE is promising to do something similar. And that is that, from what I understand, I'm not an expert on this, but the KGE can give desirable results, except the flow duration curve may not show a really good match. And then with this JKGE, Mohammed in his paper shows that there's a better match for the dry and the wet years, meaning that this replaces a little bit this loss score, because if you're already getting a much better match, then that's preferred, because this loss, the gradients are so little. If you look in the paper, the values of the gradients are so minimal that it's hard to find a descent direction, so that the training is much slower. And we were actually finding that problem with this as well. Let me do an example run. It's actually quite funny. Very quickly, region, I'll check Sweden, model HPV, I think. That's all okay. Basins. Yeah. So we're going to Sweden now. This is daily data. Yeah. So I'll just go with the default attributes. And now I select the JKG, right? Yeah. Let's see if this runs. I haven't tested this combination yet. No. Okay. So what you see with the JKGE, do I have, oh, let me check one thing. Oh, I do option 2. I should have done 1. So this is a revised form, but what we see is that the JKGE has a little bit of that same tendency. You're not going to see that in this run now because I selected another formulation. So here you now see the JKG 1 minus, and you see how it performs for those Swedish watersheds. This is a revised form. When I implemented Mohammed's formulation, what I noticed is something I noticed with the flow duration curve score as well, is that it goes down initially a few iterations and then it is almost horizontal. The gradient has vanished. And what I show you now is the adjustment that I suggested to the JKG so that you don't have that problem. But my experience is as soon as you start matching flow duration curves, I found that the gradients become really small. So there must be a way around it. So in other words, that suggests if the gradients are very small, that suggests that the flow duration curve may not be that informative. That because there's no time effect, right? All the data, the time effect has been taken out. So that suggests that you can simulate the exact flow duration curves in very different parts of the parameter space. So this disaggregated in time. And I think, I mean, we can do a lot of analysis on that. But yeah, I understand your point then that once you start looking at CDFs and entropy is the same thing, that your binning method, how you treat the data, how many, that's extremely important. And people never talk about it, very little. Whereas these details really matter. Anyway, I don't know what I'm showing now, but you see with this this is the new form, but we're still working on this essentially. Let me stop that.
So we're probably a good time to stop, but I think it's very exciting because it's clear that this gives us a framework which allows us to leverage and build into the future a lot of things that were very hard to do before, but become so much easier and possible to do now by combining this with modern large language model capabilities and so on. So I'm very excited about where the future is going, which allows us to essentially revitalize hydrology, where we're not just looking at machine learning prediction solutions, but we're actually hoping to learn something more about hydrology by incorporating the hybrid between the two. Yeah.
I agree, Hanshin. I agree.
Exciting to me.
No, I agree. And it's wonderful to see that you're so actively engaged and involved. That's really, to me, very inspiring. That, it's such a joy and the energy you still have and the ideas and all that. So thank you. There's also something else that I think maybe something to think about is that we try to pursue in terms of funding or something as a team instead of competing against each other. Maybe we can try to to do something as a team together. I think that puts us in a much stronger position overall, not only against all the AI companies, but Jonathan, I've talked about it recently, and in hydrology, there doesn't seem to be much of a legacy or so where people really do things in large groups. It's really teams always competing against each other or individuals competing against each other. And I noticed that I like to do stuff alone or with students, but ultimately I would really enjoy working with other people, in a team, like working on different aspects instead of everyone doing their own stuff, right? Because when you go to these meetings, there's no synergy, meaning people run their own models, their own code. It's been going on for years, and there's all kind of reasons for that, but that makes it really hard to find where the progress is or to have a common benchmark. It's, yeah. Anyway,
No, absolutely. All right, let's all
thank you.
thank Jasper here. I think he deserves
Thanks, Jasper. That was
A
really
a
good.
round of
round of
applause.
applause.
Oh, thank you.
That was
I hope it
incredible.
made sense.
Thanks for taking the extra time. And
Thank
I'm
you.
sure we'll come back to this and have a lot more conversations about it. Especially now that you've shown that we can start doing this interfacing with intelligent design, right? Large language models, which they're functioning more than just code writing, but they're actually allowing people to do hypothesis building and testing and so on. Because it
Oh,
takes
yeah.
a lot of the work, a lot. Otherwise, you have an idea, but you think, oh my God, it's going to take me 3 years to do that, right? Or what Jonathan told you, and then you show him, no, if you do this, it dramatically speeds up everything. Yeah.
Now, I could put last 5 seconds. What I would like to develop, like here you see a PDF. I already made it so that MATLAB or whatever language prints this on the screen. But what I like it to be is that you can just click here, you place a reservoir here, and then you place an arrow there, and that based on whatever you put there, that the whole thing is done. But that is
Yeah.
a lot of work.
Well, there are some examples. So this is where we need the team that you're talking about.
Yeah,
If you look at Simulink in MATLAB,
yeah,
that's essentially a framework for doing that, right?
yeah,
And if you approach it from the point of view of neuroevolution of augmenting topologies, you know that graphical description has a genetic description, and that genetic description has a meaning and can be read in by a Turing machine, in this case your code, and it can spit out the implementation that's computational, right?
yeah.
And so then that brings us back to information theory, because now you can start to impose, you can start to use description length as a guide to to model development. If you only have a little bit of data, you use a simple representation. But as you get more and more and more data, your implementation, your description of the system can grow proportionally to the amount of information that's available, which is what science really is about doing, right?
Now that's very interesting how you never thought of it. But indeed, you could represent this figure as just a DNA sequence, right? And hydrologic
Exactly.
sequence of, and that's all we communicate then. And then based on that sequence, you provide here as an BitLocker code, right? Then the computer just does the rest, essentially knows exactly what you want.
Yeah. They've already demonstrated that you can use that approach to build LSTM type models or generic machine learning models, but which are modular, so that they're more interpretable. That means each module has a particular function, but it takes advantage of the function approximation capabilities. But it writes you a model which where if you perturb something, it has a meaning. So a lot closer to a scientific implementation. What humans always prefer models that are modular and descriptive. Yeah.
No, great.
All right, guys. Thank you again, Jasper. That was really wonderful.
Thank you.
I guess Leela will post the video at some point because there are several people who went off who wanted to listen to the discussion afterwards. So we'll come back to this discussion, I'm sure.
And one day, hopefully, I have my slides that I can actually teach the steps properly, the math behind it. But it takes a few hours
Okay.
to really understand
Yeah.
the individual steps. But thank you.
No, that's actually something that's worth thinking about, and we might consider as an information theory group actually hosting and promoting a lecture series where you could do that, and we could invite more people to participate. It would bring attention to our group, and I think it would be a nice way to help build larger teams also.
I agree. I agree.
All right, thanks, guys.
Thank you, Ocean. I hope you
Thanks
feel
for
better
sticking
Thanks,
it out.
everyone.
I just want to say hi, Abdul. Oh, well, he's gone. He's a student who's just getting into this from a U of A. It was nice to see that he was here. Yeah. All right.
Good.
Thank you,
Bye-bye,
Leila.
everyone.
Thank you, Dan.
Thanks.